Hello all, my name is Mrinal Kaushik and I am the faculty in Aerospace Engineering at IIT Kharagpur. Under SWAYAM program, I am going to take the lecture actually that how to teach the course called High Speed Aerodynamics. It is also termed as Gas Dynamics. Okay. So, essentially when we are given this course to teach the students, most of the students they find it very difficult. They say this is a complex subject. We have to ensure as a teacher that this subject is not at all complex. Only thing is that we should keep in mind that all the students in the class, they are not having the same background or same intelligence level, and they do not have the same fundamentals as well. So, just to generate the interest among all the students, we should give the adequate information about any topic whichever we take up, and then subsidiary mathematics applications. As a teacher, we should also stimulate their interest by giving some examples, the modern trends. So, coming back to the subject which is we are going to discuss about the gas dynamics or high speed aerodynamics. Let us begin here. We keep hearing the term like or we keep crediting in our curriculum fluid dynamics, fluid mechanics, we say aerodynamics, we say gas dynamics, rarefied gas dynamics. What are these? How could the flow or flow regimes, that is the fluid flow in fluid in motion, actually are given these many terminologies? Let us see this thing, and this same thing we have to tell to the student that what are these? They are all discrete, or they are all same, or what are the differences? Why these many nomenclatures actually? Let us begin like this thing. As we know from our school physics days actually, that the matter has the three states: solid, liquid and gas. Solids are those that by definition, that whenever you have a shear force, that is a tangential force, let us say if this is a solid object, a cube, let us say suppose, and if you give the shear force, then it will resist the force applied. That means the solid object try to oppose the motion of the direction where you are applying the force. That means as soon as you remove the force from the object, the solid will come in its natural state again. But if you take up a cube of a fluid, let us say fluid lump, and then if you apply a shear force along the fluid by definition does not resist the shear force. Then what it does do? What it does actually, that you apply the force and the fluid, that is the liquid, let us say first the liquid gets deformed continuously. The same thing happens with the gas. That is why both liquid and the gas, they are clubbed into the term called fluid, and that is why they are together studied. This is in contrast to the solid, where the physics which deals the solid, it is called solid mechanics. Here, when the fluid is at rest, and then we discuss all these properties associated with the fluid, we commonly termed as fluid mechanics. But practically, it's theoretically all the fluids are stagnant, but in practical situation or many engineering applications in various engineering fields such as aerospace, mechanical, chemical, the fluids always are in motion. So, the regime which studies the motion of the fluids are termed as fluid dynamics. Okay. Moreover, these fluid dynamics are categorized in various flow regimes based on some properties. What are they? If we talk about the properties, let us first begin with the thermodynamic properties. We know from the thermodynamics aspects, any state of the fluid can be fixed by three thermodynamic properties. They are pressure, temperature, and density. The density, which is very much important for fluid dynamics. Why? Because essentially in all these regimes, that is the fluid dynamics, aerodynamics, and so on, in these regimes, the density of those fluids are studied which are solely dependent upon pressure. In general, out of these three properties, that is the pressure, temperature, and density, any of them can be written in terms of other two properties to fix the state. But when the one parameter is weak, however, another parameter is strong in defining the third property, then it is a matter of more interest, and that is what we are going to talk about. Likewise, let us say we choose that we want to see the changes in density. So, from this explanation what I just spoke, that we can write down that rho is equal to rho of function of, that is a function of pressure and temperature. Whenever the temperature is a weak dominance of changing the density, but the pressure is having more dominance in changing the density, then we can write down, or we can say that density is alone the function of pressure. These kind of fluids are termed as barotropic fluids, and that is what our main interest here lies. That means, if the density is changing with respect to the pressure, that is, if we change the fractional or increase the pressure, the density is changing, then we say this is a barotropic fluid undergoing the density change. It is not the case that the temperature is not acting, but the change of the density with respect to the temperature is very, very small, and we can ignore it, or that is not our objective, and that gives the other flow regimes like we used to hear incompressible flow, fluid flow, compressible fluid flow, and it has been seen that if suppose in the fluid flow the 5% density change, because which is more or less a worldwide accepted condition for engineering practical limit 5 to 8%, generally it is accepted that if the density change of 5% is there in the fluid flow, we should say yes, density is changing, and then we say this is a compressible liquid. That means if we are applying the force, we say that density of this fluid is changing. So, the 5% taking as a criteria, we can say that the change in density lesser than 5% belongs to a flow regime called incompressible flow, while a density change of more than 5% is termed as compressible flows. Now, this 5% criteria belongs to, we can associate it to some flow properties. The first flow property is that since the fluid is in motion, then it is related with the speed. You will see it practically during many experiments that as high as 30 to 40 meter per second, this corresponds to about 5% or 7% density change. Therefore, the speed range up to, let us say, 40 meter per second, the 40 meter per second, we can say this is the 5% change in density. So, all the flow which is below the 40 meter per second, we can say essentially that these flows belongs to the incompressible flow. More than 40% the density change, we say this is a compressible flow, because now here slight change in or fractional change in pressure, the density is changing. This leads to a very important parameter called compressibility factor. The compressibility factor is defined as the change in fractional volume of the of a fluid with respect to the change in pressure, and generally it is denoted by beta. And when you are changing, that is, you are compressing the fluid, there are two ways of compressing the fluid. That means either you can do it using keeping the temperature constant, or that is termed as isothermal, and then the compressibility becomes isothermal compressibility. However, if you are doing it keeping the entropy constant, that you are not allowing any disorder into the system, and then when the change in the entropy of the system is not taking place, or it is more precisely called isentropic process, then this compressibility factor becomes isentropic compressibility. Then in aerospace engineering, if we talk about, what I have given is a general engineering application, but in aerospace, rather than speaking of flow speed, we talk about a non-dimensional number that is called a Mach number. The Mach number essentially the ratio of the flow speed, or that is the object speed, divided by the speed of sound. That means it comes from the ratio of inertial forces to elastic forces, and when in the doing the non-dimensional analysis, it leads to the ratio of V by A, where the speed of the object is V and the speed of the sound is A. Then this Mach number, if we take back to our discussion that 5% change in density, then this Mach number corresponds to 0.3, about 0.3. So, but technically it is worldwide accepted among the scientific community that this 5% change in density is termed as less than 0.3 is termed as incompressible flow, more than 0.3 is called compressible flow. Now, as we left out the temperature effect so far, so what essentially we can say that from theoretically 0, that is fluid at rest, up to Mach number 0.3, the temperature effects are ignored for this barotropic fluid. But it is not always true that you can ignore the temperature, because temperature also is a thermodynamic property and it affects the density. Therefore, if you are having a situation where temperature is changing, then let us take that again you are taking as an engineering practical limit of 5% and you are changing the temperature. Then changing the temperature of a flow situation or a flow regime under consideration more than 5% and less than 5%. This 5% criteria, which is termed as delta T by T in the percentage, gives another aspect that where the governing laws of the flow regimes, what are they? The continuity equation, or more precisely conservation of mass, continuity momentum equation second, that is conservation of momentum, conservation of energy or energy equation, and second law of thermodynamics, and obviously the first law has to be valid. Out of these, when we in the fluid mechanics up to Mach 0.3, the conservation laws which deals the flow regimes, analyze the flow situation, are basically the conservation of mass, conservation of momentum, first law of thermodynamics and second law of thermodynamics. But since the temperature change in the flow regime is not appreciable yet, hence we ignore the temperature effect, and hence generally energy equations are not considered. But as soon as you have more than 5% temperature change in a fluid flow, then you are bound to have the energy equation in your analysis. Generally in aerospace sciences, where we are interested in flying objects, aircraft, spacecraft, missiles, ammunition during the war time, which are the launched from your aircraft, ships, that is all the flow field which is are of beyond the normal speed. It is termed as about 650 km per hour, which essentially corresponds to the 5% temperature change. And in terms of more precisely in the Mach number, as far as aerospace applications are concerned, this comes around 0.5. That means all the flow regimes which are more than 0.5, the temperature changes are appreciable. They are termed as high speed flows, and all the flow regimes which are below 0.5, we tell a low speed flow. But here, as a teacher, we should emphasize here at this point so that the student can grasp. Please note that we just said, while distinguish from incompressible to compressible fluid flow motion, we said Mach 0.3 is the criteria of from changing or transition of a regime from incompressible flow to compressible flow. But for the low speed and high speed aerodynamics, we say this is called a flow situation, that is Mach 0.5 actually. So, all the fluid flows more than 0.3 but lesser than 0.5, we say that the flow is compressible but low speed, and 0.5 onward we say it's a high speed flow. Naturally, these are the compressible flow situations.